Okay, so today we will start about the week 3 problems. So that is depend on the dynamic strain aging, PLC effect, and uh, precipitation hardening. So we'll start with the questions. So first question is on what defines the phenomenon of dynamic strain aging. Means what is the dynamic strain aging? So uh, dynamic and strain aging is the time given to any material, and dynamic strain is some deformation is done to any material or sample. So dynamic strain aging, like in the stress strain diagram, when we load a sample, unload it, and keep it for some days or some week and some months, and then again reload it, so the strength. So this is the yield point initially, but after aging, the yield strength appears at high stress. And if we further increase the aging time, then it also the yield strength also increases. So the change in change in yield strength with the aging is the dynamic strain aging phenomena. So it can be written as loading, uh, loading the sample, then unloading it, then reloading after aging, uh, increases the yield strength during, and also high stress is required during deformation. So this phenomena is known as the dynamic strain aging DSA. Okay. So next question is what why does the flow stress of a material generally increase as the strain rate increases under normal condition? So with increase in strain rate, yeah, so first we'll understand what is the deformation. So behavior. Like for deformation, we need to move the dislocations, and dislocation move when we apply any stress with applied stress. And for a certain deformation, or if it wants to surpass any barrier in its path, so it needs some type of energy, it needs to overcome some energy barrier. So, like this is the dislocation, this is the energy barrier, and it has to move from this to this point. So, the energy barrier have two components. First is the applied stress. This is the applied stress sigma, and this remaining part of this barrier is thermal activation. So under normal condition, when we do not apply some temperature, or we do not increase the temperature, so the thermal activation could not achieve uh, for for the deformation. Only applied stress is there. So we need to apply more stress, more. We need to apply more load to overcome this barrier using not in the normal condition. So to overcome this barrier, more stress need to be applied. So that's why higher stress is in strain means strain rate increases as a strain rate increases under normal conditions. So with increasing strain rate, the dislocation velocity increases with increasing strain rate E dot. The velocity of dislocation also increases. So it has to overcome the barrier as soon as possible because the strain rate we have increased. So we have to apply more stress to overcome the energy barriers in the path of dislocation motion. So that's why we need higher flow stress. So stress is applied stress is higher. So the flow stress of the material in the deformation process also increases when we increase the strain rate in under normal condition. Okay. So next question is, what is the physical cause behind the appearance of stretcher marks on the surface of a deformed metal? So stretcher marks are the means deformation bands. Means in deformation band we know that this dislocations are moving and they accumulate at grain boundaries, interfaces, and uh, free surface. Free surface is the sample surface. So, and at the free surface in any boundaries or interfaces, the dislocation accumulate and they make it some type of slip uh, because of the slip of the atom planes. The some small deformation bands generate at the free surface because of atomic plane motions. So if it is high at deformation is higher and the dislocation density is also high, so the because of the deformation, the means the deformation is only constrained at in that area of the sample. So the deformation bands create at the surface, generate at the surface because of atomic plane displacements. So that's why the stretcher straight marks appear on the free surface of a deformed metal. Next question is, how does the waiting time of dislocation at obstacles change when the strain rate is increased, and what is the consequences of for dislocation movement? So, as the strain rate is increased, means deformation rate is increasing. So we know the strain rate can be given as rho b v, where rho is the density, dislocation density, b is Berger vector, b is Berger vector, and v is the velocity of dislocation. So velocity can be written as, means if we want to move dislocation from this point to this point, so this is L, and so we have to move L distance in time t. So This can be written as rho B L by T. So in the time T, there are two times. One is the waiting time, sorry, L by, so one is the waiting time and one is the flight time. So flight time is that time when dislocation moves. So waiting time is generally larger than the flight time because in during flight the dislocation move fast with increasing dislocation. So with increasing strain rate, so TF is very less than TW. Waiting time is larger than flying time. So this can be written as rho B L by TW. So there is inverse relationship with waiting time and strain rate. So waiting time decreases when we increase the strain rate. So because the waiting time is less, the uh, activation barrier is high. So the stress generally increases for the motion of dislocation to maintain the strain rate. Next question is, in the context of plain carbon steels, what is blue brittleness and why does it occur in a specific temperature? So blue brittleness is the means brittleness is 100% and there is no ductility at that point. So blue brittleness is loss of ductility completely. So yeah, we know that the dislocation motion need the thermal activation also. So with thermal activation, uh, plain carbon steel we have in the plain carbon steel we have some interstitial elements. So interstitial atoms move fast at high temperature and lock the dislocation easily. So the deformation will be hard. Deformation will be tough for the plain carbon steel because the dislocations are locked by the interstitial atoms. So so, so yeah, with so this diffusion of interstitial atoms happens at some temperature range. Means in that temperature range, the diffusion is highest. So that temperature range is 225 degrees Celsius to 375 degrees Celsius. So in this region, uh, the dynamic strain edging happens. So that dynamic strain edging, the higher stress we have to apply for motion of the dislocation because the temperature dislocations are locked by the interstitial atoms. So that reduces the ductility of the uh, plain carbon steel and leads to blue brittleness. at this temperature, diffusion is very high. Diffusion of interstitial atoms is highest. And at higher temperature, means if we increase the temperature above 375, so that the thermal activation or dislocation motion is achieved. So that's why the thermal activation, because of the thermal activation and applied stress, the dislocation can move easily and free from the interstitial atoms. And the slip systems also increases uh, with increasing the temperature. So that's why the only the dynamic strain aging happens in this temperature range. What is the effect of increasing the strain? So next question is, what is the effect of increasing the strain rate on flow stress when dynamic strain aging is not occurring? Yeah, so this is the same as the some previous last discussed question. So with when dynamic strain aging is not occurring, so the with increasing strain rate, the flow stress also increases. Like this is at epsilon dot 1, and with increasing strain rate, epsilon 2 dot, so E2 is greater than E dot 1. So seventh question is, why does the flow stress decrease with increasing strain rate during the occurrence of dynamic strain aging? So in dynamic strain aging, DSA, the solute atoms could not catch the dislocations with increasing strain rate. Hello. Yes. 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 Yes, I started. Okay. Surinder, can you see my slides? Yeah, so why does the flow stress decrease with increasing strain rate during the occurrence of dynamic strain aging? So with increasing strain rate, the solute atoms could not catch the dislocations with increasing strain rate because the waiting time is decreased with increasing strain rate. So the solute atom could not diffuse to the dislocation and catch them to stop the dislocation motion. So with during dynamic strain aging, the uh, as the strain rate is increased, the flow stress decreases during the dynamic strain aging. So the flow stress because the solid atoms could not catch dislocation uh, in the dynamic strain aging regime. So flows flow stress decreases. Eighth question is, what does the pinning theory? What does the pinning theory propose regarding the relationship between flow stress and strain rate to explain serrated flow? So pinning theory is the means concept of strain so, means the flow stress with versus strain rate. So that uh, uh, describe the phenomena why the serrated flow happen during the deformation. So this is the uh, sigma versus flow stress versus strain rate curve. So the dynamic strain aging happens for a certain strain rate range. So up to let's say if dynamic strain aging appears in this range of strain rate and uh, means before this and after this strain rate there is no DSA. And here no DSA will be. Here also no DSA. Okay. So we can write A some point and this is point at B and then let's say this point is this point it is C. So between A and B, one point is there where so let's say if we apply the strain rate is epsilon A, which is between the A and B point. So this is the C point. So for this condition, the strain rate is defined as Sorry, the flow stress of the material can be written in terms of strain rate and strain. Sigma as a function of strain rate is written as sigma equals to sigma naught plus h epsilon plus sigma epsilon dot strain rate. So h is the strain hardening coefficient. So when we differentiate this equation with respect to time, so that can be written as sigma dot d sigma by dt equals to h e epsilon dot plus d sigma epsilon by dt, and this can be written as d epsilon by d epsilon. So d sigma epsilon divided by d epsilon is the strain rate hardening, means this term is the strain rate strain rate hardening, and h is the strain hardening coefficient. So this equation, so when strain rate the hardening d sigma epsilon dot by d epsilon, means if strain rate hardening is zero in dynamic strain, say it is zero, means d sigma epsilon this and by d epsilon dot. So the slope of point A at A and B is this point and A is this. So at A and B, the strain rate this slope of the curve will be zero, means the strain rate hardening is zero. So when it will be zero, the strain rate will be, means the change in strain rate will go to infinite at A and B. So that we can write the equation further, means this can be written as, yeah. So d epsilon by dt will be E dot. So we can write it further. E double dot will be sigma dot minus h E dot divided d sigma epsilon dot by d epsilon. So when it will be zero, this E dot will be will be infinite, means the strain rate will increase to from the initial strain rate. So when so this is at C point, we have the applied strain rate. So for the applied strain rate, the stress increases up to the A point, and as it reaches to the A point, the strain rate hardening goes to zero, and this goes to infinite. E dot goes to infinite. So the strain rate increases to this point. But the the applied strain, we have to maintain the applied strain rate. So we have to again go backward in this path. Let's say it is F point. So from F to B we are going, and from B to C we have to go. So, but at B point, the strain rate hardening again goes to zero, and uh, strain rate changes. So as it comes to point B, it again goes to the flow stress decreases to deform the material. So this at this stress it reaches, but the flow stress for the required strain rate is at this point. So it again the stress again increases up to a point, and this uh, process continues again and again, and that leads to the formation of serrations like this. And strain goes s- sigma versus, so this is the sigma means stress versus strain. This is the strain rate curve, sigma versus epsilon dot, but this is the sigma versus epsilon. So this behavior we experience when the dynamic strain aging exists. So again, so this question is complete. So this is the pinning theory. Next question is, what happens to the strain rate at points of maximum and minimum stress in the strain stress strain rate curve according to the pinning theory? So at the maximum and minimum point, the that E dot goes to infinity because the strain rate hardening is zero. So at A point, if the strain rate increases, and when it comes to B point, because because the strain rate applied is high, so deformation flow stress is and this is under the dynamic strain aging region. So because of the dynamic strain aging, the stress decreases as it comes to point B. So at maximum point A, the strain rate increases. So it is epsilon dot A. This is epsilon dot 1, epsilon dot 2 increase. So from epsilon dot 1 to epsilon dot 2, it reaches. At minimum point, as we uh, as we so the minimum point is at B, so the and it is under the dynamic strain aging region. So during the dynamic strain aging, flow stress is decreasing. So at B point, flow stress decreases. then so next question is, what is the defining characteristic of strain rate sensitivity? Characteristic of strain rate sensitivity when dynamic strain aging occurs. So this is the strain rate behavior, means the change in flow stress with respect to strain rate. So strain rate sensitivity can be defined as change in flow stress sigma with change in strain rate. So this is called as strain rate sensitivity. So the in dynamic strain aging, uh, so this can be written as sigma equals to K epsilon dot, this is K epsilon dot raised to power M. So the M is the strain rate sensitivity parameter. So it can be written as M equals to d of ln sigma divided dl of ln strain rate. So the value of M is less than 0 when dynamic strain aging occur because the flow stress is decreasing with increasing strain rate. So the M value will be less than 0. And if there is no strain, dynamic strain aging, mean it is not in the range of that strain rate or temperature. So the flow stress increases uh, with increasing strain rate. So M will be positive. Next question is, how does the propagation behavior of the localized deformation band differ between type A and type B serrations? So the serrated flow is also of three types. First is, and this again means the stress is increasing step by step, and this serrated flow occur at higher stress level. So this is a type A. And at B point, at type B serration, so this is type A, type B. So in type B, uh, the serrated flow is at the same delta sigma value, means the change in delta sigma is same. So the type A serrated flow uh, is the when type A occur when the deformation band move continuously through the specimen. So this deformation band motion is the so this is the continuous motion, but it disappears at this point and appears at this point again. So this correspond to disappearance of a band and initiation of a new band. So for initiation of a new band, the flow stress is increased. And in the type B serrated flow, it is the uh, so the deformation band uh, it hops from one position to adjacent one and continues to move further. So one serration means one jump or hop. Next question is, why do aluminum alloys typically exhibit a critical strain for the onset of serrated flow compared to the interstitial solute-based steels? So, in interstitial solute-based steel, the interstitial atoms are very small in size as compared to the iron atoms. Interstitial atoms are very small in size, while in aluminum alloys, so this is for steel, and for aluminum alloys, there are no interstitial atom, only substitutional atoms are large in size. So interstitial atoms can move for any level of stress applied, but for aluminum alloys, we have to apply some stress. So deform the metal deform little bit up to a certain level of strain, and then the serrated flow start. Means after the yield, we can say it after yield point, it started. So the diffusion of the interstitial atom is higher than substitutional atom. That's why the because the diffusion is low, we have to generate some strain level. Then the serrated flow starts in aluminum alloys. So for this, a critical strain is required to start serrated flow. So critical strain is written as epsilon C. Next question is, what is the effect of increasing the temperature on the observed critical strain for serrated flow, and what is the underlying physical reason for this? So as we increase the temperature, the diffusion normal has to be increased. Temperature diffusion also increases, means diffusion rate increase. diffusion rate increases. So the diffusion rate is increases. So the substitutional atoms can easily log the dislocation and generate the serrated flow. So because of the increase in diffusion rate, the critical strain required for serrated flow decreases. Yes, we can see the this is at T1. So this is at T2. So the critical strain is decreased with increase in temperature. So what does changing the strain rate influence the transition between serrated types A, B, and C? Yeah, so the strain rate have inverse relationship with the critical strain value. Means if we increase the strain rate, the critical strain also increases. Yes. So this is at the epsilon 1 dot and this is epsilon 2 dot. So epsilon 1 is less than epsilon 2. So with increasing strain rate, the the substitutional atom could not catch the dislocation easily, and for serrated flow to start, we have to increase the deformation further. So the critical strain increases. So we know that there are three types of serrated flow, and the if we want to write the so if we need a relationship between the strain rate and temperature, so a graph ln epsilon dot by 1 by t, it follows two graph. So between these two lines, between these two lines, there is dynamic strain edging occurs. And above this there is no DSA, and below this also there is no DSA. And the uh, serrated type flow is at this line is the A, and at between the DSA it is B, and at this point it is C. Yeah, so type C is the this type of change in stress with strain. So for some strain level, the flow stress is same and this drops at some points. Okay, so in the type C, there is no propagation uh, of deformation band of bands. Means the propagation of deformation bands do not occur, and the new deformation bands appear at each time on the surface. Band nucleates on specimen surface. So this is the C type. So with decreasing the strain rate, the A to A, this serrated flow changes from A to B to C. B is the normal serrated flow in the dynamic strain aging range. And with increasing temperature, with increasing temperature means in this direction, the A, B, C occur. So from this uh, uh, figure, we can say that with increasing strain, uh, sorry, with the decrease in strain rate, the serrated flow changes from A to B to C. And with increasing temperature, the A to B to C occurs. So when strain rate decreases and temperature increases, so the substitutional atoms have enough time to catch the dislocation and pin them. So the serrated flow changes from A to B to A is the where a higher flow stress is required each time. Then B is the normal serrated flow at a constant delta sigma value, and C is the uh, separate appearance of deformation bands at the surface. Okay, so this serrated flow means serrated flow behavior. So next flow behavior and dynamic strain edging. Edging phenomena is given by Portevin LC, means the Portevin Leclerc scientist. So that's why this phenomena is known as the PLC effect. So this is the 15th question answer. Means what is Perturbing PLC effect? So it is the serrated flow only in dynamic strain aging. Next is next question is, how does temperature affect the critical strain for serrated flow? So this is the same. Mean with increasing temperature, the critical strain decreases for serrated flow. Why? Next question is, why does the magnitude of serrations delta sigma increase with strain? Yeah. So yeah. So as we increase the strain further and deformation continues, deformation increases, and with increase in strain, the vacancy concentration also increases. And this vacancy concentration increases the diffusion rate further. And diffusion rate is increased because of the vacancy creation. So the solute atoms can pin the dislocations easily, and the uh, stress required to move the dislocations because of the locking of solute atoms, we have to apply more stress. So that's why the with increase in strain, sigma and epsilon, the delta sigma means the difference between upper and lower point increases. with increase in strain value or deformation. It, 18th question is what are the primary mechanism proposed for magnesium diffusion in aluminum at room temperature? So we discussed the means strain rate behavior, temperature behavior, in and strain rate behavior and waiting time of dislocation at the solute atom. But how does this magnesium diffusion occur in aluminum alloys? So magnesium atom is larger than aluminum atom, and because it is large, it wants to go in the below the dislocation plane. Means this is the dislocation plane. So above the dislocation, there is compressive region, compressive stress field, and here below is the tensile stress field. So it diffuses from compressive to tensile region, and from by doing this diffusion from upside to below, the magnesium atom can easily log the dislocation. So this is the lattice diffusion. So this occurs by the lattice diffusion. Means there are atoms arranged above and below the plane. So because of the lattice diffusion, magnesium atom move, moves in tensile stress field. Okay. So, but there is one more type of dislocation which one more type of diffusion which is called as the pipe diffusion. So pipe diffusion is occurs from the porous dislocation to mobile dislocation. So porous dislocation provide the path from the dislocation core. So we can see that this is the dislocation plane where atoms are arranged, but at the dislocation core, the magnesium atom sits. So if there are multiple dislocations, it is let's say it is the forest of dislocation. So there will be means the core concentration dislocation core will be very high in density. So the magnesium atom move from core to core dislocation cores to reach the mobile dislocations in the material, and the catches the dislocation easily and faster than the lattice diffusion. Diffusion is slower than pipe diffusion because the forest dislocation helped in the motion of the substitutional atom through the dislocation cores. Pipe diffusion is higher. So that's why the in pipe diffusion, the magnesium atom could easily catch the dislocation. So there are two types method. One is the lattice diffusion and second is the pipe diffusion. Next question is what industrial methods can be used to prevent the occurrence of dynamic strain aging? So dynamic strain aging means we have to apply more stress and the deformation is not regular. So we need to avoid this strain and temperature region. because the dynamic strain aging DSA occurs for a certain strain rate and temperature. So only a certain region of strain rate and temperature give rise to dynamic strain aging. So first point is that we have to avoid this strain rate and temperature range. Second is uh, we can provide some deformation uh, techniques to avoid the dynamic strain aging. So first is the uh, leveling or temper rolling. So in leveling, we use small dia rollers to move back and forth on aluminum sheets. So the deformation provided by this process uh, means increases the dislocation motion and cannot solid atoms cannot catch the dislocation and could not under the deformation in between. In the temper rolling, small reduction is given to aluminum component, small reduction in the cross section of an knee. So it is around zero point 0.5 to 1.5%. So providing small strains in the aluminum sheet or any component, we can avoid the dynamic strain edging behavior because the because of this deformation, the other slip systems also activates and the deformation continues without any hindrance from substitutional magnesium atoms. So next question is, what is the fundamental requirement for an alloy to be considered precipitation hardenable? So this is based on the precipitation hardening. Precipitation hardening is that some precipitation is occurring in aluminum alloy that increases the strength and hardness of that aluminum alloy. So the major precipitation hardenable alloy are 2000 series, which is aluminum copper, in which Al2Cu uh, precipitate form. In the 6000 series, aluminum silicon magnesium Mg2Si form, and 7000 series also heat treatable aluminum zinc. So all these alloys, aluminum alloys, form precipitates. So these precipitates hinder the not hinder, yeah, in hinder the dislocations and increases the required flow stress for the deformation. So stress means the strength of the material increases. So for the precipitation to happen, we need the lower solubility at low temperature and high solubility at high temperature. Means the solubility in aluminium should decrease with decrease in temperature. So as the solubility decreases, the precipitates form from the this solid solution of the aluminum, copper, aluminum, silicon, magnesium, and aluminum zinc. Precipitates form by this process. Okay, so this is the fundamental requirement, means solubility in aluminum should decrease with the decrease in temperature. Next question is, why is a high cooling rate necessary after the solutionizing treatment? So solutionizing treatment is that treatment where we uh, means this is the phase diagram. So we have a material at this point. So we need to first to make the complete solid solution to up to maximum concentration. So this is the maximum concentration. So this is at T1 and this is at T2. So first, so this is the solubility is decreasing with temperature. So we increase the temperature to get a supersaturated solution. This is the solutionizing treatment. And after the solutionizing treatment, we quench the material, the sample to room temperature. So quenching is the cooling the sample at very high rate, means the high cooling rate we use. So with high cooling rate, the means there will be no segregation of the solute atoms from the aluminum matrix. So the higher solubility maintained at the low temperature. Now after the quenching, we apply some temperature or keep the sample at room temperature only. So temperature should increase high up to uh, 200 degrees Celsius or room temperature. S- So, if we left the sample at some 200 degrees Celsius or room temperature, the copper atoms or the solute atoms diffuse from the aluminum matrix slowly and form these precipitates Al2Cu with different diffusion rates, because at temperature the diffusion will be high and at room temperature the diffusion is low. So with this process we can make the fine precipitates, because in the mechanical properties fine precipitates provide the best strength. That's why we need high cooling rate. And if we do not cool it at very high rate, so the copper will diffuse, and if some precipitates form, that precipitate will be coarse in size, and the coarse precipitate will are not good for the strength. So what happens? The next question is on the what happens to the precipitate size and hardness if the cooling rate from the solutionizing temperature is too slow. If the cooling rate is very slow, the precipitate form for by the heterogeneous nucleation on grain boundaries. So at grain boundaries, these precipitates are forming, and also they are in coarse in size. So this leads to the intergranular fracture. Means the fracture will occur from the grain boundaries. And intergranular fracture means the less ductility and the poor mechanical performance. So we do not need our material to fail from intergranular fracture. So that's why we avoid the low cooling rate. And so the precipitates are uh, coarse in size with low cooling rate, and the hardness also reduces if the cooling rate is slow. Next question is, what are the three core stages of the precipitation hardening process described in the lecture? So first is the solutionizing, second is quenching, and third is aging. Aging is when we keep the material at some temperature or at room temperature. First, second, and third. So there are three. These are three stages for precipitation hardening process. Next question is, how can the TTT time temperature transformation diagram help explain the formation of equilibrium phases versus supersaturated solid solution? So let's make the TTT diagram. So this is time versus temperature. So uh, this is temperature and this is time. So at solutionizing temperature, the complete alpha solid solution is there, and with the decreasing temperature, the phase transformation occur by this curve. So this is starting of the formation of the second phase. So this is at alpha aluminum, and at this point, the Al2Cu starts to form. So this is at 1%, and this is at 100% line. Means when it reaches this point, this will the complete transformation or complete precipitation will occur, and somewhere between this is 50% line. So this is the transformation lines, phase transformation. So if the cooling rate is slow, so with temperature is decreasing slowly with time. So if this is the cooling rate, the L2Cu form, and it will be coarse in size, precipitate. And if the cooling rate is very fast, at this point. So this is high cooling rate. Sorry, this is low cooling rate. Low. And this is high cooling rate. So the precipitate will be finer, fine precipitates. Okay, so these are the question. We will discuss the assignment question also. So first question is strengthening of aluminum alloys through elastic interaction is mainly due to. So in elastic interaction, the solid atoms interact with the compressive and tensile stress field around the dislocation. So third option is correct. Second is in elastic interaction, strain field associated with substitutional solute atoms will interact with. So in elastic interaction, the substitutional atoms interact with the compressive and tensile stress field of edge dislocation. So second option is correct. In the third question, electrical interaction between solute atoms and dislocations arises due to Uh, sh- so the electrical interaction occur because of the difference in valency. So solute of different valence act as charge center and attracted by the dislocation core. So fourth option is correct. Fourth question is which of the following statement is correct about the stacking faults in metals? So higher resistance to dislocation motion if width of stacking fault is less. No. High stress to dislocation motion if width of stacking fault is more. Yes. Means stacking fault uh, energy gamma is it can be written as Berger vector divided by distance between these stacking fault. So as the dislocation width is high, energy is reduced. So we have to apply more stress to move the that dislocation partial. So higher resistance is required when if width of stacking fault. No, higher resistance is less. First option is correct. Next is higher width of stacking fault results in the lower stacking fault energy. So C option is correct. Then formation of the stacking fault in FCC metals is equivalent to form thin HCP regions. Yes, this is also correct. Means the FCC metals have atomic arrangement as ABC, ABC, and so on. So if we move, if we replace the C plane, so it will be ABAB, C, A, B, A, B, and C. So the ABAB structure is of HCP metals. So the stacking fault changes. That's why fourth option is also correct. Next question is the stacking fault energy is directly proportional to separation between partial dislocation. No. Inversely proportional to separation between partial dislocation. Correct. Inversely proportional to Berger vector. No. It's only B option is correct. Fifth question is the alloying element is mainly responsible for yield point phenomenon in aluminum alloys. Yield point phenomenon means dynamic strain aging. So magnesium atom generally uh, give rise to the dynamic strain aging. Seventh question is which of the following statements are correct in case of strain aging phenomenon? So at upper yield point, that dislocation will be able to break free from the solute atoms. This is correct. In case of strain aging, so this is not strain aging. At upper yield point, dislocation will be pinned down by the solute atoms. Yes. Due to strain aging, yield point reappears at a lower stress. Yes. Because of no, this this is strain aging. In dynamic strain aging, the real point reappears at higher stress, lower stress. But for normal strain aging, real point reappears at higher stress. This occur at dynamic strain aging. Eighth question is if the processing temperature of the alloy increases, means if we increase the alloy process deformation, so mobility of solute atoms increases. Yes. Dislocation velocity increase. So because of the increase in mobility of solute atoms, the dislocation velocity decreases. Yeah, but the dislocation velocity also increases with increase in temperature because the thermal activation is there. Dislocation velocity decreases only when the uh, dynamic strain aging is there. Ninth question is region of disorder created by movement of dislocations in superlattice is called as, so superlattice is long range order. So in the long range on order when dislocation move, it creates antiphase boundaries. We discussed in the previous lectures also. The 10th question is which of the following mechanisms are related to the solid solution hardening in aluminum alloys? So solid solution hardening occurs from the modulus interaction and interaction of solute atmosphere and dislocation. So B and C is correct. Some more questions are there. First is the reappearance of yield point will be much earlier if the material is allowed to age at temperature more than the room temperature. Much earlier if the material is allowed to age at room temperature. So because at room temperature the diffusion is low, so dislocation cannot be pinned again by the solute atoms. So at room temperature, the yield point will appear easily if if the aging is done at room temperature. Second is which of the following are associated with dynamic strain aging? So in dynamic strain aging, the serrated flow occur, the solute atmosphere present in the material, and the solute atmosphere log the dislocation. So the PLC effect is there. So B, C, and D is correct. Next question is serrated flow in the aluminum alloy occurs at a strain rate of, so the PLC effect in aluminum alloy, which is typically aluminum magnesium alloy. So the strain rate value is 10 raised to power minus 2 to minus 5. So first option is correct. Fourth question is serration type changes from A, B, C with So with the ABC change in sedation occur when strain rate decreases and temperature increases. So increasing temperature and decreasing strain rate. Second option is correct. The strain aging process in terms of movement of solute atoms varies with time t as. So in this is based on the week 2 lecture. So it is around t raised to power 2 by 3. First option is correct for this. The second next question is the alloying element is mainly responsible for yield point phenomenon in aluminum alloys is magnesium. In aluminum magnesium alloy only the yield point phenomenon occur. Seventh question is the atomic jumps are more frequent along. So atomic jumps occur when the solid atoms comes in contact with stress field around the dislocation core. So at dislocation core, the stress is higher, and as we move away from the dislocation core, the stress decreases. So the atomic jumps are also in the from the dislocation core to away from dislocation. So means and with in decreasing stress, the energy also reduces. The direction of decreasing energy. Third option is correct. Eighth question is onset strain at which serrated flow starts will appear early. So epsilon C depends on temperature and strain rate E dot epsilon dot. So with increasing temperature, we can reduce the critical required strain for serrated flow. So when temperature increases, the onset of strain serrated flow can be achieved. Serrated flow in the aluminum alloys can be avoided by so serrated flow occur because of the solute concentration. So if we decrease the solute concentration, the serrated flow can be decreased. Then say third option says that in testing the material by avoiding the range of temperature and strain rate where serration can occur. So third option is also correct. Serrated flow cannot be completely avoided in aluminum alloys. No, this is not correct. Means we can avoid the serration in the aluminum magnesium alloy to by avoiding the that temperature and strain rate region. Tenth question is difference between the maximum and minimum stress during serrated flow will decrease with delta sigma. It increases with time. Increases with temperature and decrease with solute concentration and decrease with strain rate. So decreasing solute concentration and decreasing vacancy concentration reduces the diffusion and locking of dislocation. So first is correct. Second is incorrect. Increasing temperature and decreasing strain rate. No, this is wrong. Decreasing temperature and increasing strain rate. So this is correct. So first A and D is correct. So this is all for today. We'll meet in next lab. Sorry, next week.